continue with the talks about the roles and research trends of some spaces of function related to solution of PDEs.
Thanks again to all of you, especially to the organizers, to give me this opportunity today again. Thank you very much. Yesterday we end our talk considering some relations between two different moral spaces. Just to fix and recall some spaces that probably for someone are new and that we will not see in any slides, I write in the blackboard some definitions that time by time we need. Such a way we have this in front of us and can easily follow the properties that we will show. These properties are relations between different kinds of spaces in such a way, if we have some regularity results for resistance for PDEs in one space, we can understand if are for free in other spaces or not. So we like to compare the spaces in such a way we can study easily the relations between the qualitative properties of the solution. So yesterday we recall the definition of Murray class. Let us consider P between 1 and infinite and lambda between 0 and n. N more or equal 3 from now on. Omega a bounded open set in Rn. So a Murray class is a class where is found the following quantity. The supremum if f is such that x is in omega, rho between 0 and the diameter of omega, and of the following quantity. 1 over rho with exponent lambda, the integral in omega cap bx rho x of fp y dy. So, let us now consider this set. And what we said yesterday is that the relation between two Murray spaces is the following one in the slide. So LQ mu is contained in LP lambda, where Q, mu, P, and lambda are in these relations here. Also, we define the weak Murray spaces. The space is denoted by LP lambda omega, and is the set where is found the following quantity: the supremum if t is more than 0 of the measure of the set of x in omega cap bx rho x0 rho of the absolute value of f more than t should be less or equal a constant c independent on rho and the fixed point x0 times rho lambda. Let us now stop here. Later we need some other definitions that I have just write, so we will talk about them later. Yesterday we considered the relation between a Murray space and an LP space where the exponent is different. So we proved that, and we finish with this, that LP is, if P is more than n over 2, if P is more than n over 2, we have that LP is contained in L1 lambda for every lambda between 0, the n minus 2, and n. These and a lot of other inequalities that compare the relation between these kind of spaces are based on Helder inequalities. Indeed, if we consider the integral in omega cap bx rho of u, using Helder inequality, we have that is through this first line here. Then, of course, we have that the first quantity is the norm of u in LP. Then we have that the exponent of rho is n times 1 minus 1 over p, and we have that u is in L1 lambda. This is true, of course, where lambda is exactly equals to n times 1 minus 1 over p. Well, because of p is more than n over 2, we have that n minus 2 is less than n times 1 minus 1 over p. This is less than n, so it's easy to prove that, bearing in mind the absolute continuity of the integral function of up, we have that u is in L1 lambda, and then the proof is completed. Probably I need the lighter. If it is, I could use it. Well, thank you very much. Okay, so now we are interested in the relation between a Murray class and a weak Murray class. I have just recalled what is the Murray space here and the weak Murray space. What we obtain is that if we have p more than q, both more or equals 1, and lambda between 0 and n, we have that LP lambda weak is contained in L mu, where q, I said, is less than p, and mu is n minus q multiplied by n over lambda over p. The idea is to, in general, to consider a function here and prove that it's in this space. So let us consider that f is in L. We have to prove that f is in L mu. So we start with the integral of f with exponent q. Well, so we have, using a property that could be found, for instance, in the celebrated book of Gilbert and Schrödinger, we have that is true this inequality here. Now we share the integral between 0 and plus infinity in 0 epsilon, some epsilon, plus the integral in epsilon plus infinity. So the first integral between 0 and epsilon could be majorized with q, epsilon with exponent q, rho n, the measure of the set. Then the second integral between epsilon and plus infinity could be majorized with this quantity q, rho lambda, and the variable t with exponent q minus p over q minus p. This calculated between epsilon plus infinity gives us this quantity phi epsilon. And then minimizing in epsilon this quantity, we have exactly that we have that the integral in omega cap bx rho of fp is less or equal a constant that is dependent on p and q times n with exponent n minus q times n minus lambda over p. Then the conclusion is obtained. So this is the idea for this comparison and other similar comparison with other spaces. Let us now recall what we consider as VLP lambda. I've not written here because it's quite easy to remember. We have that. This is the space LP lambda. The vanishing LP lambda is the space where this quantity is not only infinite but tends to 0 as the radius of the pole. Okay, so what we have is that if q is more than p, a function u in LP is such that it is in vanishing Murray class LP lambda, where p is less than q and lambda is exactly n times 1 minus q over p. Well, let us prove this new result. Let f rho more than 0, then what we have? As I said before, we start from the thesis. We consider u with exponent q. Well, the integral in omega cap bx rho 0 rho for a generic x0 in omega is such that is through this Hölder inequality. U with exponent p, because we apply Hölder inequality with exponent p over q and the conjugate. Then we have the integral in omega cap bx0 rho of up with exponent the quantity q over p times the mention of the dimension of the set, so rho with exponent n times 1 minus q over p. Then, if this, I said, is exactly lambda, we have obtained that this is less or equal rho lambda times the integral in omega p x0 rho of up over q over p. So, this is nothing else that, bearing in mind the absolute continuity of the integral of u with exponent q, that we arrive to the conclusion. Then we have also the relation between a Morey class and Lebesgue class and the vanishing one. Now I would like to show you another kind of possibility to study the regularity results, for instance, in Stummel-Schechter type spaces. Let us now define this class. Let us consider u a summable function and omega as before set in Rn. So let us consider the function eta r equals to the supremum of for x in omega, or the integral in the set of y belonging to omega, such that the absolute value of x minus y less r is the set where we consider the integral. Then the function that we put inside is u in absolute value over x minus y, and I point out that now is not a generic lambda between 0 and n, but is exactly n minus 2. This is the new set we will consider, that is defined as Stummel-Schechter space. Briefly, we indicate this as S tilde omega. In the case that we have that the function is also infinitesimal where r tends to 0, as the vanishing Viale, we consider only this as S omega. Okay, so later we will consider sometimes S tilde and sometimes S. S is that one where the integral function tends to 0. Well, if f is a summable function in omega, the fact that the function eta r is finite in a point is equivalent to the fact that it is finite in every point r more than 0. And this is true because let us consider r more than 0 such that eta r is finite. Well, from the definition of eta r, we have that it's clear that if it's finite in r, is finite if rho is less than r. So we have that, of course, that eta rho is less or equal eta r. So let us fix now x0 in omega. Then for the compactness of the space, the closure of omega cap b, something more than r, 3 over 2 r, I say here 3 over 2 r, it's possible to find x1, x2, xp such that the set omega cap b with radius r over 2, 3 over 2 multiplied by r is contained in a sum, in a union of some sets, p sets, that are omega cap br x1, x2, xp. Well, then let us consider the integral in the set of x belonging to omega such that x0 minus r is less than 3 over 2r of the function f over x0 minus 2 with exponent n minus 2, or equivalently I put everything here with exponent 2 minus n. Then what we have, because of this consideration here, we have that this quantity is less or equal the summation for if j is from 1 to p of this integral in the sets of y belonging to omega such that xj minus y is less than r in absolute value. The function is the same. Well, let us consider these singular integrals as capital Ij, and let us estimate this Ij. ij could be shared in two integrals. The first one, where I point out that x0 minus y is more or equals xj minus y. The second one, when x0 minus y is less than xj minus y. Well, let us consider these two, and we call capital AJ and capital BJ. Let us prove that both are finite. So AJ and BJ really are finite because we have that are both less or equal the integral when we consider x in omega such that xj minus y is less than r and x0 minus y is less than r. So these are finite. Also, if we observe that the number p of the sphere depends only on the ratio of the radius, because in the case where we have considered at the beginning 3/2 times r, therefore what we obtained, that the quantity eta in 3/2 times r is finite, hence we conclude, of course, this could be considered not only for 3/2 but for every different r. Then I like to compare this kind of spaces with the Morrey class. The chain of inequalities is this one. L1 lambda, the Morrey class with p exponent 1 and Morrey exponent lambda, is contained in S. I remember that S is when tends to 0 the quantity. This is contained in the quantity in the space S tilde, where is only finite the quantity. Well, this is contained in L1 mu, where the relation between lambda and mu is the following one. Lambda is between n minus 2 and n, and mu is less than n/2. Both, of course, strictly more than 0. Some one of these is trivial. Of course, it's trivial this one, this in the middle. Also is trivial this one. What we have to really prove, and this is, of course, because this in this space the quantity tends to 0, and here is only bounded. Well, now let us prove the first one. But the probably is more interesting the last inclusion, because the first one is a consequence of the definition of the space. So the really interesting case is the last inclusion. Let us consider a function f that we put in the integral. So we have the integral in omega cap bx rho of u. Now multiplicating and dividing by x minus y with exponent n minus 2, because we force to obtain something like this. So we need the function over x minus y with exponent n minus 2. So what we have, that this integral in light blue here could be majorized with rho, and we put out of the integral. Then it is only this fact, but this is consider equivalent to consider rho mu and rho with exponent minus mu. Then what we have, that this is less or equal a generic constant that we can put every time, rho, and it's useful, with exponent mu, and the integral in omega cap bx rho of the quantity that we need for the Schechter space, u over x minus 1 with exponent n minus 2. So now we have, considering dividing both sides for rho with exponent mu, we obtain the first inequality, the first inclusion. Therefore, let x and rho generic, so x in omega and rho more than 0, what we have that the integral in the set of y belonging to omega such that the absolute value of x minus y is less than r of the function u over x minus y with exponent n minus 2 could be shared using the method that is called as onions method. So we share in some separate thin slides the set, and we have the set could be considered as separate as union of the following one: u in omega such that x minus y is between rho with exponent 2 with exponent k plus 1 and less than rho with exponent 2k. So these slides as an onion of the set give us the possibility to do the following majorization. Let us consider this quantity in here, x minus y with exponent n minus 2 less or equal rho over 2k plus 1 with the same exponent n minus 2, because we use the left part of this set. Then we have the integral if y is in omega such that x minus y is less than rho with exponent 2 over k. And we have in the integral only the function u. Then what we have? Multiplication and dividing by rho with the denominator 2 with exponent k lambda, that we obtain here 1 over 2 with exponent n minus 2 and the summation between 0 and plus infinity of rho with exponent 2k n minus 2, because we here are not interested in 2 with exponent 1 because it's not in the series. We are interested in the part where we have k. So we consider this quantity plus 1 here before the series. Then we consider 1 over rho with exponent 2k lambda, and of course we have the presence of this lambda because we have here the equivalent in the multiplication. So the exponent n minus 2 is here, and what we have, we can majorize what is in the real in the series is a constant, because we have exactly this. We copy again 1 over 2 with exponent n minus 2, then the summation between 0 and plus infinity of the quantity 1 over 2 with exponent lambda minus n plus 2 with exponent k. Of course, we have to remember the relation between lambda and n minus 2. This is fundamental. And rho with exponent lambda minus n plus 2, and the norm of u in L1 lambda. So what we obtain, that is the series is convergent. Then we have a constant with multiplied by rho with exponent lambda minus n plus 2 times the norm of u in the Morley class L1 lambda. So the convergence of the series is guaranteed, of course, as I said before, because of lambda is more than n over 2. And here is from here was born the idea to consider only this restriction for the Morley exponent lambda. Another class of function that we will consider is the Schechter space MP. MP is written here. MP is recalled later, but now we give the definition. Let us consider omega inner n more or equal 3, a bounded open set, NP as usual between 1 and infinite, but could be 1 and could be infinite. Well, what we have is that a function f, a summable function f, is in the Schechter space NP if is find the following quantity: the integral in omega in the x over 1 over p, and the integral in omega cap, the set where x minus y in absolute value is less than delta, of fy over x minus y with exponent n minus 2, and this with exponent p. So I copied it here because later probably changing the slides is not so immediate to recall it. This is should be found for some delta more than 0. Well, we briefly define this not only MP omega but MP. So it's easy to prove that if MPF is finite for fixed delta, it is finite for every delta more than 0, and this is similar to the previous remark we just today proved. Also, we point out that is interesting the case where P is more than n over n minus 2. Indeed, if a function f is in L1, then f is in LP for every p less than this quantity n over 2. And also, we use later the quantity where p is infinity. Indeed, this is called M infinity, and is a supremum if x is in omega, such that x minus y in absolute value is less than delta of the function f in absolute value over the absolute value of x minus y with exponent n minus 2. So if this quantity is finite, is M infinity, this is MP with these two exponents p and 1 over p. So I have not written M infinity because probably it's a little bit simple. Okay, so we can observe that we have that if we compare this M infinity and the Stummel class as tilde, where this is only bounded, not tends to 0, the spaces are the same. So now what we ask, of course, when we define some class of function, we would like to know the relation between one and the other. So in this theorem we can see the relation between all this class of functions. So we have that if q is more or equals p, and q is contained in MP, all are contained in M1, and M infinity is contained in all. If you see, of course, similarly to the Lebesgue spaces, L infinity is contained in LQ, contained in LP, contained in L1. And this is the basis because we obtain this chain of inequalities using Helder inequality. Indeed, let us consider f, a function f, and we consider at first the integral in the set where x minus y is less than delta of the quantity absolute values of f over x minus y with exponent n over 2. Well, let us consider we like to obtain this kind of functions here. So we start from the inside integral, then we have the, if we consider the m1, so the integral in omega of the integral in omega cap bx rho of fy over x minus y with exponent n minus 2, using Helder inequality, we have that we need a constant here, that is a dimension of the space, times this integral in omega of this function here with exponent p, and all with exponent 1 over p, only using Helder inequality. But this is because of, we remember the relation between the exponents p and q, we have that is true this inequality here, where we have that the L the P quantity is less than Q. So we copy the same quantity with exponent Q and all over 1 over Q. Now let us consider that this is less or equal the supremum, if X is in omega, of the quantity that is inside. So if you think, we have concluded our proof, because we obtain the relation between M1 and MP and Q and M infinity. Let us now announce an inclusion theorem between Schechter and Morley class, not only the Schechter's spaces. So what we have is that if we, as usual, omega is in n and more or equal 3 is a bounded open set, and lambda is between n minus 2 and n, we have here, look, the relation between the Morley class and the MP class. So L1 lambda is contained in M infinity, that is contained in L1 n over 2, and all this is contained in all the sets MP. Indeed, I write here to write that are in all MP, that is in the intersection of MP for every P between 1 and infinity. So some one of this is simple. We have that M infinity is S tilde. So we have proved this first relation here. What we have to prove is that also this is true, but what we have to prove is that L1 lambda is contained in a P for every P. This last line is equivalent to this one, the last inclusion, because here we have nothing else that L1 n minus 2 is contained in MP for every P. So it is in the intersection. Okay, let us consider P between 1 and plus infinity. What we need is an instrument that we will see later, that was proved by Chiarenza and Frasca concerning the Ritz potential in Morley spaces. We will see the proof of it later. This result will be later shown, and what we have is that if we have that lambda is between 0 and n minus 2, and f is in L1 lambda, f is in n minus 2 is in L1 lambda, so that we apply the following result that I show is that is the Ritz potential is in a weak Morley class. The result is this one. So the details of this inclusion, this belonging of the Ritz potential in this weak Morley space will be later proved. Then I2f is the integral in all the set omega of f over x minus 2 with exponent n minus 2. So if we have this relation where we have that q lambda, the labeled exponent here, q lambda is such that 1 over q lambda or equivalently 1 over q is 1 minus 2 over n minus lambda, because we recall a theorem where it's called only q. Okay, what we have is that the weak space L q lambda lambda omega is contained in L p mu, where the relation between all these quantities is that p is between 1 and 2 lambda, and mu is n minus the fraction where we have p times n minus lambda, and in the denominator q lambda. So in particular we have that the Ritz potential I2 is in LP for every p between 1 and q lambda. Well, what we have, if lambda tends to n minus 2, we have that q lambda tends to plus infinity. And so we have proved the conclusion. Now we would like to slightly change a kind of class of spaces, but is useful in the PDEs and is used a lot, is named BMO, where BMO means bounded mean oscillation, because for instance in some PDEs, as I mentioned before, the simplest and classical one, summation ij between 1 and n of aij x u xi xj equals f. In this kind of simple elliptic equation, non-divergence form, is well studied the regularity result when f is in a Morley class LP lambda or some similar spaces that we showed before, and the coefficient, the highest order coefficient, the coefficient of the highest order derivatives are in some class of this. So now the picture is complete if we define where aij are. F is in Morley class or variant of them. aij are in BMO or similar. But first we need to define the BMO class. BMO means bounded mean oscillation. This class was at first defined by John and Nierenberg in the paper titled On Functions of BMO, published in Communications on PDEs in 1961. So, in this paper, they defined this class. Let us now define it. Let us consider U a locally summable function and Q a cube with sides parallel to the coordinate axis. So, let us set as a tool UQ the mean integral of f of U in Q. And define U star as the supremum where Q is contained in Rn of 1 over the measure of Q, the integral in Q of Ux minus this mean integral. If this quantity is finite, U is in BMO or has bounded mean oscillation. So there are some studies where aij are in BMO. So, but what I wish to start to point out is that L infinity is not contained in BMO. So we can prove that exists functions that are in L infinity but not in BMO. Why? For example, let us consider a function U that is bounded in a cube Q with sides parallel to the coordinate axis. So what we have, if we consider the definition of BMO, we start with this definition here. So 1 over the measure of Q, the integral in Q of Ux minus UQ. But this is a constant. So we can consider this as with the triangular inequality Ux plus UQ. Then this is 2 times 1 over the measure of Q, the integral of Q U. 2 times because 1 is this if we put before the integral. So what we have, that this is a constant and the norm of U in L infinity. Then what we have, if we consider the supremum of the cubes over the set of cubes in Rn, that this quantity is less or equal the norm of U in L infinity. So, on the other hand, exists a BMO unbounded function. And we wish to show you an example of it. Let us consider this function here. I forget here the graph here, but the function U is clear that is considered with three different values. 0 if the absolute value of x is more than 1. Minus logarithm of x of answer if x is 0 and 1, of course is trivial the absolute value, but is necessary here logarithm of x in the set where x is between -1, 0. This function is unbounded, and we can prove that is in B and O. So we really have proved that is through this inclusion. Then, for all the spaces before introduced, it is possible to define the local version. So we can say that the local version in a subset of omega, of course, and we can have local regularity results. How long time I have? Now I have time because I have a quarter. Okay, perfect. So I like to start with the integral operators. The end of this chapter is to estimate singular integral operator and commutators. So let us give some preliminary tools. In this paragraph, we study the action of some integral operators in the Morley classes. That is motivated by the application of these results to the regularity of solutions of PDEs, as I said before and also yesterday, of elliptic type, parabolic type, ultraparabolic type, and system. So we start to define the Hardy-Litour maximal operator. We said that F is a real measurable locally summable function in Rn. Then for every x in Rn, we consider the set of function u such that 1 over the measure of b rho, the integral in b rho of fy in absolute value, if rho is more than 0, is considered. If this set is upper bounded, we say mf, the supremum of this kind of quantities, if rho is more than 0. And we say that mf is the maximal function of Hardy-Litour, and this is very, very useful in the applications because we can obtain that the representation formula of the solution u or of the derivative of the solution can be expressed in terms of maximal function and other functions that we will see. So this is the maximal function of Hardy-Litour, and the application that associate to f the function mf is say maximal operator. So later we will call of maximal operator. The first result is the following one, through the following implications. The first is that if f is summable, we have that the measure of the set where the maximum operator m is more than t is less or equal constant c over t multiplied by the norm of f in the Lebesgue space L1, and this is true for every t. If f is not in L1 but is in L infinity, so is bounded, the norm infinity of the maximum operator f is less or equal the norm infinity of the function f. And if f is not in L1, is not in L infinity, but is in Lp for every p between 1 and infinity, we have that mf is less or equal f in the Lp norm. So these three relations are the first step to understand the relation between a function and a maximal function. The proof of these are classical and are, for instance, contained in the book by Stein that I mentioned here, Singular Integrals and Differentiability Properties of Function, that is published in 1970, but also it could be possible to find these results in the paper by Torczewski, Real Variable Method in Harmonic Analysis, later published in 1985. Both are classical books where these relations and all the Schechter inequalities could be found. A variant of the maximal Hardy-Litour operator is the fractional maximal operator. So let us define the definition of the fractional maximal operator. Let us consider eta between 0 and 1 and f a locally function in Rn. So the fractional maximal operator is the function m eta f, so we have the present, because of its fractional in eta here, of the supremum rho more than 0, 1 over the measure of b rho with exponent 1 minus eta, times the integral in b rho x of f. This function here is said fractional maximal function of Hardy-Littlewood. Look here the present of minus eta here for every eta between 0 and 1. So the function that is associated to this is named fractional maximal operator of Hardy-Littlewood. So only m is the maximal function, fractional is with every eta between 0 and 1. So as the maximal operator of Hardy-Littlewood had some boundary properties from LP spaces, similarly for the fractional operators we have similar properties, based most of them in the good use of the Hölder inequality. So if we are expert in manage Hölder inequality and change the exponents, we obtain the relation between a lot of these spaces. For instance, the first result is the following. Let us consider f a function that is p summable, p between 1 and eta of 1 over eta between 0 and 1, then we can prove that the fractional operator m eta is bounded from LP to the weight LQ. So LQ omega, where 1 over p is equal to 1 over q, 1 over q is equal to 1 over p minus eta. So we have to start the proof. The assumption is that f is in LP, p between 1 and 1 over eta. So without any restriction, because of this in LP, the norm in LP is finite. We can consider the normalization function that so we suppose that for simplicity that this quantity is equals 1. Well, using Hölder inequality we have that 1 over the measure of b rho with exponent 1 minus eta integral in b rho x of ft dt is less or equal some other quantities. But before I continue this proof, I would like to show you that the method that we use for these inequalities is several times the same. So what we have is that M is bounded from LP to this class. Well, we have to obtain this boundedness, and we use Hölder inequality here. Well, now we continue the proof. So we have that this is less or equal. We copy again 1 over the measure of b rho with exponent 1 minus eta. Then we multiply using Hölder inequality to p1 over p, the first term, the integral, and because of here we have only f, we consider that here is for example 1, and we have the measure of b rho with exponent 1 minus 1 over p. So the conjugate exponent. This could be considered exactly like this, and we have 1 and 1 that we can delete, and what is in the next inequality is minus 1 over p here, but if we consider the measure in this part of the fraction, we have plus 1 over p, and we copy minus eta. Well, now we consider this quantity here, this copy, plus for every epsilon between 0 and 1, the measure of B rho with exponent epsilon minus over P. And if we choose this quantity epsilon 1 minus eta over, times P, we have that we can majorize the first term with the maximum function of Fp with exponent 1 minus P minus eta, 1 over P minus eta. So, what we have obtained, if we consider here the maximal function, so the supremum, we have that m eta is less or equal m, but here we have m eta f, and here we have m eta fp with the same exponent. So, from this inequality and the previous theorem, we have that the measure of the set x in Rn such that m eta f is more than lambda is, of course, less or equal the measure of the set where the function in the second member, m fp, is more than lambda with exponent minus 1 over P minus eta. We have this inequality. If this is more than lambda, the first term here, this one, is more than lambda. But we can multiply for the reciprocal quantity of this, and we have minus 1 over P minus eta here. This set here, the measure of this set, is less or equal the next quantity here that I put up a constant C times the norm in L1 of Fp, because we know the relation between weak spaces and LP spaces, so the weak space is less or equal than the LP, and we have here 1 over this quantity, 1 over P minus mu minus eta. Then it's equivalent to consider a constant multiplied by lambda with exponent minus 1 over 1 minus P less eta, Fp P. Then what we obtain from the comparison between the first set here is that if we multiply it by the reciprocal of this, we have lambda with exponent plus this quantity in the first member, less or equal a constant C with the norm of F in LP with exponent P. So, this is equivalent to consider, as before we defined the quantity Q, so we consider lambda with exponent Q multiplied by the measure of the set where the fractional integral operator m eta f is more than lambda, less or equal a constant times the norm of f in the Lebesgue space LP. So if we consider here the comparison, we have exactly what we announced in the statement. So we have the comparison between more and weak spaces. And as a remark, it's possible to improve the above results using the Marcinkiewicz interpolation theorem. Indeed, if we consider P equals 1 or P equals 1 over eta, we have the fractional integral, fractional maximal operator is between L1 to L1 over 1 minus eta weak space, and M eta is between L1 over 1 minus eta L infinity. For the Marcinkiewicz interpolation, we have that M eta is defined in LP and with values in LQ for all the set P and Q. Then, another operator similar to the maximal operator introduced before is the operator associated to every function fx, locally summable. This is named sharp function. The sharp function is the following one. Let us define it with this symbol here. So this is the supremum if rho is more than 0 of 1 over the measure of B row, the integral in B row of the absolute values of Fy minus F row, where who is F row? F row is the mean integral of F, of the values, absolute value of F, in the ball centered in X with radius rho. So if we do not consider F row, we have simply F in N1 in the set B row. So the presence of minus F row define the sharp function F sharp. We recall this later as F sharp. This operator was introduced in 1972 from Pfefferman and Stein, and precisely in the book, in the paper of Pfefferman and Stein titled HP Spaces of Several Variables, published in Matematica in 1972. So, now we are interested to recall some results about this kind of functions, the relation between the maximal function and the F sharp function. The relation is explained in the following theorem. Let us consider the maximal function in some L P0 Rn, where P0 is an exponent between 0 and plus infinity. So, it is possible to prove that for every P more or equals P0 and less than infinity, then exists a constant C that depends only on N and P, such that the relation between these two functions, maximal function and sharp function, is the following one. So I point out here that is exactly the same P exponent here, the same LP space. Now we can now study the action of the maximal operator introduced before in the Murray class. So what we can consider is now MF in LP land. We know from these results, these classical results, the relations in LP. In the second part of the lecture of today, we start with the relation between MF and F sharp in the Murray class LP land. So this section will be probably after lunch.
Yes.
Okay, thank you very much.
Thank you very much, Professor Ragusa. Maybe some comments? Question?
Yeah, so in the space NP, yes, I guess that the n represents this is x minus y and minus between minus 2.
Yes.
This is the fundamental solution of the Laplace operator.
Yes.
What's the critical case if n equals to 2, this inclusions became true, or?
No, we cannot apply all this all theory, so it's not included in.
Because it can be logarithmical.
Exactly, the theory is the approach should be different in that case.
Ah, I see.
Someone else? If not, thank you very much again, and we will continue after.
Yes. I can let it here.
Yes.
Yes.